Hello, and welcome to Lesson 6 of this Introduction to Linear Algebra with Wolfram U. The topic for this lesson is linear independence. So let's begin with a brief overview of the lesson. So here you see there are two vectors, a pair of vectors in this picture over here, and one of them is red, the other one is blue, and they clearly lie along the same straight line. And in such a case, we'll say that they are linearly dependent. On the other hand, if you look at this pair over here, then they do not lie along the same straight line, and we have a term for that. We say that they are linearly independent. So this lesson studies the topic of linear independence for sets of vectors, not just in 2 or 3 dimensions, but in n dimensions. So let's begin with a formal definition of linear independence. So vectors v1, v2 up to vm are linearly independent if the equation c1v1 plus c2v2 up to cmvm equals 0 has only the trivial 0 solution. What that means is that if you put all the constants over here equal to 0, then of course you do get a solution, but that's the trivial 0 solution. And the question is, are there any other solutions or not? Well, on the other hand, if you say that things are linearly dependent, then what you mean is that there are constants c1 up to cm, not all 0, such that the equation is satisfied. And this equation over here is called a linear dependence relation among the vectors v1 up to vm. And this relation is actually a homogeneous vector equation. The word homogeneous just means that you've got a 0 on the right hand side. Okay, so now some simple examples. So let's say you have a set with just one vector. Well, if you have a set with one vector, then it is linearly independent if that vector is not the 0 vector. So for example, here's the vector 2, 4, 7. And if you try and figure out the linear dependence relation, it says that c1 times v is 0, 0, 0. But of course, that just means that you only have c1 equal to 0 as a solution. So it only has the trivial solution c1 equals 0. And therefore, the set is linearly independent. Now suppose that you have the 0 vector. Well, then you can choose any scalar like c1 equal to 5, and then if you do c1 times v, you do get back 0, 0, 0. So this set is linearly dependent. So for a single vector, it's really simple to figure out whether the set given by it is linearly independent or not. So let's go on to sets with 2 vectors. Well, if you've got 2 vectors v1 and v2, then that set is linearly dependent if at least one of the vectors is a multiple of the other, a bit like what you saw in the figure early on. So basically what you need is that you want, for linear independence, that neither of the vectors is a multiple of the other. So for example, here you got v1 equal to 2, 3 and v2 equal to 4, 6. So clearly v2 is twice v1, and hence this set is linearly dependent. On the other hand, if you take 2, 3 and 4, 15, then that equation for linear dependence has no solution, no non-trivial solution, and hence the set is linearly independent. Okay, so suppose you have a more general kind of situation where you got sets with 2 or more vectors. Well, a set of 2 or more vectors is linearly dependent if at least one of the vectors is a linear combination of the others. So you can write one of them in terms of the others using a linear combination. And so for linear dependence, what you need is that some vector in that set is a linear combination of the other vectors. So for example, here you have v1, v2, v3. And clearly, if you look at v3, then it is v1 minus 3 times v2. So for example, 11 minus 6 is 5, etc. And you can check that now, that v3 is v1 minus 3 v2, and hence this set is linearly dependent. And you can check that using row reduce by basically forming a kind of homogeneous system. So you just take the columns of vectors 11, 2, 5, etc. and form the matrix A, row reduce it, and you see over here that the vector variable c3 in this linear combination is kind of free. So that confirms that you actually have linear dependence for the given set of vectors. Okay, so an example for linear independence now, where you got three vectors u, v, and w. And the question is, are they linearly independent or not? Well, for that you need to solve the equation over here, the dependence relation. So you form the augmented matrix using the vectors. Look at the matrix form, compute the row reduced version of that. And what you see over here is that there are no free variables because you only have C1, C2, C3, and they are all 0. So the equation over here only has the trivial solution, and hence the vectors are linearly independent. Okay, so a couple of quick tests for linear dependence. So first of all, if you have a set of vectors which has a 0 vector in it, then that set is linearly dependent. So for example, here you got v2 equal to 0 vector, v1 is not 0, but v2 is 0 over here, then you can take a combination 0 times v1 plus 5 times v2, and you do get back 0. So this set is linearly dependent because you have the 0 vector over there. And you can confirm that with row reduce, and you see over here there's a free variable c2, and hence you actually have a confirmation that the system of vectors is linearly dependent. Another quick test for linear dependence is to look at the vectors and check if there are more vectors in the set than there are entries in each vector. So for example, if you have v1, v2 up to vm in Rn, then the m over here should be greater than the n. So for example, over here you have three vectors. Each of them has got two entries, so you've got three vectors in two space. Let's see what happens. You set up the augmented matrix. Look at the matrix form. So the columns over here are the vectors. Obtain the reduced echelon form, and sure enough, you have one free variable. And so the homogeneous equation has non-trivial solutions, and the vectors are linearly dependent. Okay, now with all this background, we come to the topic of linear independence of matrix columns. So instead of starting with vectors, let's start with the matrix. And the matrix has columns A1, A2 up to AN. So then what you want to check is what happens to the columns if you treat them as vectors. So this equation over here can be written as a linear dependence relation, and hence every time you have a linear dependence relation, you actually have linear dependence for the columns of the matrix. So the columns of A are linearly independent if and only if this equation over here has only the trivial solution. So given a matrix and given its columns, you can then try and figure out whether they are linearly independent or not. So an example of that, here's a matrix, capital A. Look at the matrix form. And the question is, are the columns of this matrix linearly independent or not? Okay, so form the augmented matrix. Here it is. Do a row reduction over here. And you see that there are no free variables. So all the constants over here are going to be 0. So there are no free variables, and hence this set of column vectors for the matrix is a linearly independent set. So basically, for a matrix, one would like to look at the column vectors and try and figure out whether they are linearly independent or not. Okay, so that brings me to the end of the lesson, and the main point is that a set of vectors is linearly independent if and only if no non-trivial combination of them gives the 0 vector. And of course, there are many quick tests for determining that. So for example, if you have a set which has got a 0 vector in it, then that set will definitely be linearly dependent. Okay, now the point is that if you want to prove linear independence, then you have to work with the homogeneous system and check that it has got no non-trivial solutions. And of course, everything I said over here for vectors actually holds for matrices by looking at the column vectors of a matrix. So that brings me to the end of the lesson, and in the next lesson we'll talk about linear transformations. But before that, do review this topic of linear independence. It's quite important to linear algebra. So I'll stop over here. Thank you very much.